All right, so today as we launch into Chapter 7, Similarity and Transformations is the title. We've already talked a little bit at the beginning of this class about the flags that you see in your textbook and lines of symmetry. We're going to talk a little bit about that as we move through and similar polygons. But in your notes, you'll see there's a few things that we need to take a look at first. So in your notes, you'll see that on the first page you have just some of the things that you will learn here in this chapter. Draw and interpret scale diagrams. Apply properties of similar polygons. That's similar kind of shapes that are closed figures with straight line edges. And identify and describe line and rotational symmetry. We talked a little bit about line symmetry already today. Now, here's some vocabulary terms that you'll want to learn as we move through this. And again, I'm looking at your notes at the end of the chapters that when you hand these notes packaged in, just a reminder, I need you to hand those in so I can see that you're following along and doing the questions on the notes and that sort of thing. So you do need to hand those in at the end of the chapter. But I'm not seeing that many of you are actually writing these definitions down on your notes. I hope that you're doing that on some kind of study sheet or cue card. But remember that you do have the opportunity to just jot down a definition for each of these as you move through the chapter, just so that all the definitions are kind of in one spot when you kind of look back to study. Okay? So what's the first thing that we want to review here on your notes? We're going to have to convert metric units. So I don't know if you remember how to do that, but on the first page there, how many of you have ever seen this? It's called the metric staircase, these metric stairs. Have you seen this before? Anyone? No? Okay. So maybe some of you have seen this before. All right. So this is new to some of you. You will learn about this in science class a lot because there's a lot of times where we have to convert between metric units in science class. But also in math class, it's important to know how to convert units. Now, what do I mean by converting units? Well, I have a meter stick here in my hand. And does anyone know offhand or look at this meter stick, how many centimeters are in 1 meter? 100. Okay, there's 100 centimeters in 1 meter. That's exactly true. And on this meter stick, I can see that we start at 0, and there's 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100 at the end here. This is exactly 1 meter. Now, how would I know that without looking at this meter stick, or if it's, there are two units that are really uncommon, like millimeters and decameters, let's say. Well, let's take a look carefully at this chart. So there are prefixes for metric units, and you know about meters, and you know about centimeters. So do you notice on this little staircase that centimeters occupies this stair right here? And this staircase is handy for converting from one unit to another. Now here, the base unit would be the meter. So this stair is kind of the middle stair, and it contains all the base units, like meters or liters or grams or seconds or anything like that that's a base meter that doesn't have a little prefix, that's a little part of a word in the front. This is the base step, okay? This is kind of where the middle is. So these steps represent factors of 10, okay? So when you go down the steps, in order to convert from, and here's an example, 1 meter is how many centimeters? What you do is when you have to go down the stairs to get to the unit that you're trying to convert to, you multiply by 10 for each step. Or a really simple way to think about this, and it's really nice that our number system is based on base 10, because multiplying by 10 means we just move that decimal place to the right one spot, one place. And if we have to move the decimal place over 1, we fill in the spaces with zeros if there's nothing there. So 1 meter, if I have to convert to centimeters, that means I go down 2 stairs, which means I multiply by 10 twice. Times 10 times 10, that's times 100. So 1 meter is 100 centimeters, because I moved the decimal place over once and filled in with a 0, over twice, filled in with a 0. Okay? So 1 meter equals 100 centimeters. All right. What are some other examples that you see on your notes package here? Convert 300 meters to centimeters. All right, well, that's pretty easy. 300 meters, I have 300, and I multiply by 10 and by 10 again. Or I move the decimal place, which is always at the end of the number if it's not shown, I move that over one spot for the times 10 and another spot for times 10. And now I have 30,000 centimeters. You see that? So if 1 meter contains 100 centimeters, then 300 meters would be 30,000 centimeters. You just times by 100. Okay? Now, you might think it gets a little tricky when you go up the stairs. That's dividing by 10, so the numbers have to get smaller. Let's think about this. You know what a millimeter is, right? There's 10 millimeters in 1 centimeter. So it's really tiny. It's the tiniest little division that you would see on a ruler or on this meter stick right here. It's the tiny little space between the two little marks that are right beside each other. So it's super, super small, okay? But if we had, let's say we had 1,247 millimeters, and that's what millimeters looks like, okay? Milli, the first M is for the milli, and the second M would be for meters. So if I wanted to convert that to meters, how many meters would that be? Well, here's what you do. And again, this is kind of a shortened lesson of this. You'll get a longer lesson maybe in a science class. But what you do is you start on the stair that has this unit, so the milli. We start on the milli stair. That's where I am. And then if I have to convert to meters, that means I start here and I go up to where the meter stair is. So how many stairs did I go? 1, 2, 3. And when you go up the stairs, that means the decimal place moves left. So this decimal place that would understood to be here would go 1, 2, 3 spots and land there. So 1,247 millimeters is 1.247 meters. Okay? So that's just a brief introduction on how you use that staircase. If you have one unit and you're trying to convert to another unit, and they're the units that are represented on this staircase, because the metric system is based on a base 10, each stair is a factor of 10. So going left, you move the decimal place left. Going right on the stairs, you move the decimal place right. Okay. All right, so here's another example that's on your paper here. How many kilometers does 3,750,000 centimeters represent? Okay, so 3,750,000 centimeters, that's a lot of centimeters, okay? So how many kilometers is that? Well, if you use the staircase, it's super easy. I start at the centi stair, and I gotta go up 1, 2, 3, keep going, 4, 5. So that's 5 stairs. So guess what? I have to divide by 10 5 times. Or I move my decimal place from here, where it is at the end of the number, I move it to the left 5 times. And that's where it lands. So the answer then is 37.5 kilometers. 37.5 kilometers. Okay, so I've got a map of Regina here, and I've drawn a circle, and up at the top, this is a radius of 1.82 kilometers. So let's see where 37 million centimeters would take us. Okay, there, let's see. That's going to be about 10 kilometers right there. So about 10 kilometers. Let's see, our city is, come on now, think. So look at that, 10 kilometers, and here's where our school is, right in the middle there. 10 kilometers, that's bigger than our city for sure, 10 kilometer radius. So that's, how many centimeters is 10 kilometers, do you think? If 37 kilometers is 30, what did we say, 3.7 million? 10 kilometers would be about 1 million. That's about 1 million centimeters. So if you walked 1 million centimeters from our school up north, you'd still be in Maple Ridge up there. Okay, where's 37? Let's see. 13, 14, 17, 18, 20, 27. Oh, look at this. Okay, what else? Come on. 37, it's 36, 37.5. Okay, 37.5 centimeters. All right, look at that now. So 3.7 million centimeters would take us to Craven, Belle Plaine, halfway to Moose Jaw there. Look at that, right? Rollo. Look at little past Rollo. That's where Dog River is. That's where Corner Gas was, right there, Rollo. So look at that. So about let's see. Do you guys know that show, Corner Gas? Okay. It's an old show. It's kind of funny. Made right here. So Rollo, where Corner Gas was about, come on now. That's about 3.2 million centimeters from us. Okay, so 3.7 million is 3.37 kilometers. So 30, what did I say it was now? I'll go back here. So 32 kilometers. What am I saying? So 32 kilometers would be about 3.2 million centimeters. Right? Anyways, there you go. Got feet. Wow, this is pretty cool. Maps, there you go, look at that. Maps. You can do a radius. You can find the area and everything too. Okay, all right. All right, TMI, too much information. All right, let's get back to the lesson. All right, any questions so far? All right, we'll get practice using the staircase, but let's move on to the next page here. All right, so that was a little intro. I should actually make a note here that one of the other things that you should know how to do is work with something called isosceles triangles. So we did talk about this at the beginning of the class off screen here, but isosceles triangles, that's a triangle where you have two equal sides, just two, right? And some of the properties of isosceles triangles, like here's one right here on the screen. If you have the 5 right here and the 5 right here, those are the two sides that are equal. That means that the two angles that are opposite those sides must also be equal. So that's an important aspect of isosceles triangle. Also, that when you add up all the angles of any triangle, they have to add up to what? 180 degrees. Yeah, 180 degrees, not 160. Okay, so 7.1. Let's get into 7.1 here. And it'll be on your second page of your notes. Scale diagrams and enlargements. Scale diagrams and enlargements. Look at these two photos that you'd see in your textbook here. All right, Pearson Math Makes Sense 9. Page 316. So on this page right here, you see two pictures, okay? A native artist here. One is definitely larger than the other, but all of the features and the proportions of those features would be similar. So for example, you know, the size of this artwork piece is bigger in the second picture than it is in the first picture. Well, so is this man's hand bigger, and so is his head, it's bigger, and this little pennant is bigger. So everything is bigger, and by the same proportion, or by the same scale, okay? So these are the exact same representations in the picture, but one's bigger than the other. So we call that a scale diagram, or an enlargement if it's getting bigger, or a reduction if it's getting smaller. Yeah. Close that door behind you too. All right, so back to our notes here. A diagram that is an enlargement, which we just talked about, or a reduction of another diagram is called, and in this space you want to put scale diagram. Okay, scale diagram. Let me just enlarge that. I'll enlarge it for you. All right, so this is a scale diagram, and I'm going to write it bigger so that you can see it, but you should be able to fit that in your space. A scale diagram. So let me get my fancy dancy shape shifter here. Let's make a triangle. Okay. Ooh. Yield sign. Okay, yield sign. Now, if I made another yield sign right here, okay, and I made it a little bit bigger, but it had all the same features to it, this would be an enlargement of the original. Okay, it's made bigger. That is that every corresponding feature in the first diagram to the second would be made just a little bit bigger. Now, when I say every corresponding feature is made bigger, that's not a universal statement. That means that that's not true all the time for every little bit. Can you guys look at this picture right here? Look up on the screen. Are there any things that are still the same? Anything that you think might still be the same from picture to picture, specifically?
Shape.
Okay, shape is the same, right? The overall shape is the same. Yes. So there are some things that are different. Obviously, some aspects that are bigger. But in this particular thing right here, there are some things that are exactly the same in both. Shape is kind of a clue there. Go ahead.
Are the angles the same?
Ah, the angles. Now, if we look carefully, the angles here are still exactly the same. And I don't think, oh, I can. So watch this carefully. If I overlap the corner angle on both of these, and I'm not sure if I let this go, if it's going to block out the other one. Ah, look at that. You see how this angle right here, that's exactly the same in both. And if I do this, that angle is exactly the same in both. So that's kind of cool. But what is different is the length of the corresponding sides. All right? So angles will be the same if it's the same shape, but it's the length of the corresponding sides that would be different. Now this is an enlargement, and of course if I made it, come on now. Oh, I don't think I can now grab this little, Okay, that one works. Oh, there we go. So if I made the second one smaller, that's a reduction. Make sense? Enlargement and reduction. Okay. Now, the blank is the relationship between the corresponding lengths in two diagrams. That is going to be what we call the scale factor. Scale factor. And I don't know if I can actually remove these little bubbles. I don't think I can. Okay. I'll have to fill them in. So scale factor, and if you can fit that in your little space there, I don't know, in your notes, you go right ahead, but if you have to go outside, that's fine too. So the scale factor is the relationship between the corresponding lengths. To find the scale factor of a scale diagram, and again, a scale diagram is same shape, but different size. And I think we should write that down here, okay? That's same shape, a scale diagram, but different size. Same shape, different size. And how we determine what the scale factor is we do a division. So we're going to divide. And this is the length on scale diagram. So length on scale diagram divided by the same corresponding length, so that's the same part of the picture, the diagram, the length on the original diagram. So it's always on the length of the enlargement or the reduction part on top divided by the length of the original. So this is an enlargement, right? Up above here again. This is an enlargement. And if I said that this was, let's say this was 4, and over here this was 8, I could calculate what the scale factor is. That means like basically how much bigger is the other one, like by what factor, or what do you multiply the length of one side, what do you multiply it by to get the length of the corresponding side on the new diagram? And the scale factor is, let's just do this up here, and you can write SF or whatever you want, it doesn't really matter. Scale factor is good for scale factor. I don't know, doesn't really matter. So the scale factor is going to be, in this case, 8, because that's the length of this side on the diagram, scale diagram, divided by its corresponding side is 4. So the scale factor is 2. Right on. So that means it's double, right? So you have all of these lengths here times 2 gives you all of these lengths here. So in this case, if this is an equilateral triangle, if these are all 4, then these would all be 8. Okay, how you guys doing with that so far? Everybody okay with that? Got it? Is this pretty easy? Right, scale factor? Good. Enlargements, reductions, excellent. Okay, example 1, let's try this one out. Find the scale factor for the following diagrams. Find the scale factor for the following diagrams. So here's the original one. Here's the original, and here's the scale diagram. So we're moving from this one to this one. Would you first of all say that this is an enlargement or a reduction? It's an enlargement. It's getting bigger. Enlarge. Large means large, big, right? So an enlargement means you're making it bigger. Awesome. So important notes, the original and the scale diagram, if you're going to be doing this, must have the same units. That's very important. The same units. Now notice that this length is given in centimeters, and this length is given also in centimeters. So that's really important for us to know. If they're different units, like 3 million centimeters, and 30 kilometers, we can't just divide those numbers. We have to put them in the same units. If the units are different, we must convert them. Okay? And also, this is another important note, that scale factors have no units or do not have units. So a scale factor is not in centimeters or meters or kilograms or whatever. There's no units. And that's because we divide those units off. They're the same units on top as on the bottom of a division, so they divide out. They cancel each other off. So there's no units. All right, so let's go ahead, knowing that now, remembering this is our scale factor formula. The scale factor here is going to be, now the corresponding sides that we have are this side and this side. Are those corresponding sides? Yes, they're the same sides in the two diagrams. Okay, they're kind of the same sides in the two diagrams. This side over here would match with this side over here. And so on, right? So which one do I put first? Do I put 3 over 9, or do I put 9 over 3 in finding the scale factor? Which one is it? I always put the scale factor measurement on top. Very good. So 9. And yes, you can include your units. I will not require you to include your units because, as you know, the scale factor will have no units and therefore they will cancel each other out anyways. So as long as you're sure that they're the same in the diagram, normally you won't have to write your units and showing your work here. But this is going to simplify. The centimeters will divide out, and 9 divided by 3 is going to be 3. Awesome. Awesome. Any questions about that? Finding scale factor. Okay. What would you say about a scale factor for a reduction? How would you describe a scale factor for a reduction? What do you know to be true about that kind of scale factor before we actually do it? Does anybody know how you would characterize that? We know what enlargement scale factors are like. There's one. Here's one. What about a reduction? Okay. Do you multiply the scale diagram by the original? Can you help me understand what? Can you tell me a little bit more about what you mean there? I tell you what. You think about that for a second. Let me just give you an example. Okay, if this was 5, and this was 2, this is a reduction, right? Yeah. Okay. So think about this scale factor. The scale factor is going to be, because this side corresponds to this side, they're not the same, but they're corresponding. We're going to have what? Is it 5 over 2? Do you always put the big one on top? No, we put the scale diagram measurement on top, so it's 2 over 5. So that's our scale factor, 2 or 5, or what's that, 0.4? 0.4. So what can you tell me about a scale factor for a reduction versus scale factors that we've seen for enlargements? What are the differences there? Yeah, go ahead.
The numerator is smaller on the reduction.
Okay, the numerator, the top number, is smaller on the reduction. Very good. Yes, I like that. Anybody else want to add to that? Let me summarize it this way. If you have an enlargement, the scale factor is going to be greater than what? Always greater than what? Greater than the original, greater than 0, not quite. Greater than 1, yes. The scale factor is going to be greater than 1. Now think about this. If we have a scale factor of 1, if we have a scale factor actually of 1, what are the two going to look like? So here we go. I'm gonna put that. This is a scale factor of 1, guys, because this is 5, and this is also 5. So a scale factor of 1 means that the scale diagram is exactly the same as the original. Does that make sense? Because the scale factor here, oops, FF, nope, SF, thank you. The scale factor, 5 over 5, equals 1. So if we have 1 as a scale factor, that's the same size and same shape. There's no enlargement or reduction. So if 1 is going to be bigger, the scale factor also will get larger than 1. You see that? Okay, the scale factor now is larger than 1. And for a reduction, the scale factor is smaller than 1, or between 0 and 1. That's where we're going at. So, there we go. So it looks like, I'm looking ahead in the notes here, looks like we're focusing mainly on enlargements here in this section. Yeah, and then reductions next. So you should notice in your notes, on the next page, we won't write it out because it's in your notes, but check this out. All enlargement scale factors are, what did we just say? They are? Very good. Greater than 1. Let's fill this part out. Greater than 1. Very good. Greater than 1. And we're going to come back and fill in some more examples. All right, that concludes part 1. We will continue part 2 tomorrow with this second page and the assignment.